America, and good evening to Asia. Yes, I will talk about the Cloud Lake project. Um, it's a bigger project we've done in Switzerland, um, using glacier organic seeding to learn more about ice process rates. You might have heard, and some parts might seen already, but there is also quite some latest developments I will present. So for everyone will be also something new. So just have to check that I can go to the next slide. Okay. So here's already a picture of our field site where we do the seeding experiments, and a bit of an overview over my talk. I will start talking about glacier organic seeding, what it is and how we are using it. Our seeding experiment, that is actually a picture of our UAV drone where we burned a seeding flare. The observation of our seeding experiments, what we learn with the seeding experiments about ice process rates in mixed phase clouds, and then we also make the connection to the modeling and see if models can reproduce our results in the field, and if we can improve the parameterization in the model. Okay, start at the beginning. What is glacier organic seeding? You need a supercooled cloud, and you inject into the supercooled cloud ice nucleating particles, INPs, which then triggers heterogeneous nucleation. And then the so-formed ice crystals start growing by diffusion, and the droplets shrink. It's called the Wegener-Belcher and Findeisen process. Can be quite efficient mechanism to transform liquid water to the ice phase. Later on, also collision grow process like riming and aggregation starts to happen. And you can quite quickly have a glaciation of the clouds and form precipitation. And yeah, glacier organic seeding was used for quite a while. On the left is an example out of the 70s. Here they used dry ice, and you see an effect how they burn a hole into the clouds. And yeah, there's also this more stratoform that is all super cool liquid clouds, and here in the middle that is also ice crystal formed by the dry ice. And yeah, clearly seems there's a strong change in radiative feedback. And it's also used for precipitation enhancement. And that is an example from French et al. From the Snowy campaign, where they seeded over the Rocky Mountains in the US. And clearly, there's a rudder reflectivity, and the seeding signal is marked with an arrow, and you nicely see where the seeding produced stronger reflectivity, so larger ice crystal, and also that form precipitation. And it was really this publication which triggered my interest in glacier organic seeding, because I think, oh, it really works, and yeah, can we use it as a tool to not do operational weather modification or precipitation enhancement, but learn about the processes involved in the glacier organic seeding, because they're important processes. We know from satellite observation that around 70% of the global precipitation originate from the ice phase processes, and there are large knowledge gaps into these processes, as stated by the World Meteorological Organization report in 2018, which leads to uncertainties in model results. So classically, how do we study these microphysical processes? So yeah, you can go into the lab, to measure growth rate, either on a single ice particle or going chamber like AIDA chamber, cloud chamber. They have many particles, and yeah, you can have a very controlled and repeatable environment, which leads you can measure rates in it, but you always have simplified conditions. For example, particularly if you're involving ice crystal, which take 5 to 10 minutes to grow to larger sizes, the sediment also down, and then even the AIDA chamber is not big enough, and wall effects become important. Or that where I come from, you go to the field, there you really measure reality. No one can doubt this. But I got quite frustrated that yeah, I only measure a snapshot of the clouds. Here's example of ice crystal measure, and I don't know how old these ice crystals are. And every cloud is different, so it's quite hard to get a general findings out of it. So there will come Cloud Lab, where we try to do laboratory-like experiment in natural clouds using glaciogenic seeding. And here's a schematic of our experiment. So in contrast to standard operation, we are using as for seeding low stratus clouds. They're quite boring clouds, which does not produce much precipitation, but they are very homogeneous and also can stay for days. That is exactly the characteristics which is very useful for us, because it gives us an initial state which is constant and is persistent also over multiple experiments. Yes, we fly then with a drone, UAV, inside the supercooled cloud. So you should not do this at home, because you probably will crash your UAV. The problem is icing. Ice accumulates on the rotors. You need more and more power to stay into the air, and actually at some point it will crash us. Actually happened also once to me when I flew a drone. Luckily, we have a de-icing mechanism, so our drone we can heat the rotors, and that melts the icing away and prevents icing, so we can fly. It was possible for us to fly 10 minutes or longer in the supercooled clouds. And at the crash day, I haven't activated the de-icing mechanism often enough. Luckily, our drone had a parachute, so it was not a complete loss of the drone, but just some damage to the housing and rotors. Yes, and we're using for seeding standard silver iodide containing flares. They are used for operational seeding to prevent hails in Switzerland, and are quite similar also to other operational flares for precipitation enhancement. Yes, and then we see the cloud, so hopefully producing ice crystals with a radar signal. And we have a main measurement site where we observe it with scanning radars, and also a tethered balloon system where the in situ measurement will be done. And this main measurement site is fixed, so we have to have a very flexible seeding platform, a drone, because we have to make sure that depending on the wind direction, we seed a location so that the seeded bloom goes over the main measurement site and can be measured by the desert balloon. But this flexible seeding or flying platform also allows us to adjust distance between the instrument, for example, and which is the growth time or the residence time of the seeding particle and seeded bloom. So that is again the picture from the beginning of our field site. So you see here's a drone with two flares attached behind the metal protection. We had a second drone for aerosol measurements, also used the POPs instrument, an aerosol spectrometer. the tethered balloon on the ground for in situ measurements, and a lot of remote sensing instrument. We are very happy to have some partners which contributed massively with instruments, in particular cloud radar. You never can have enough cloud radars on a field campaign, so our peak was 5 cloud radars at 3 different wavelengths, but normally we had 2 Ka-band radars to observe the changes in the cloud. Yeah, we were located in the middle of Switzerland between Zurich and Bern, and did 3 field campaign, not this winter, but the 3 winters before. And yeah, now we are happy with the data, but I can say the first 1.5 campaigns, we had not really good data, not at all. And most of them was then done starting in January 23. So yeah, quite a frustrating start in the project, but quite a dramatic change, and we got much better data with more experience. Okay, did we actually, could we see a seeding signal? We were also not sure by just putting 20 grams of ice active material into the cloud, can we really change a cloud? And before I go to scientific data, I thought I start with a picture. It's sometimes stronger to see it. And on the left, you see a picture of our tethered balloon flying. Actually, you see nothing. It's in the cloud, so you only see white. But then when the seeding plume came over us, suddenly a blue sky appeared, and we also saw the balloon for around 5 minutes. That was the burning duration of a flare, and then it disappeared again. So we're very convinced that it was us doing these changes. And we also saw during this 5 minutes snowflakes coming to the ground. Here, very scientifically measured with a cup of hot coffee, also very much needed standing outside in the cold. But here, yeah, we saw very small needles only for 5 minutes, and then it stopped again. So yes, we could change the cloud. And here we come now to the scientific data, radar reflectivity plot for a seeding experiment on the 25th of January 2003. In the dashed orange line, that is where the time and height when the seeding was. The seeding flare burns for 5 minutes. And then it took around, let's say, 28 to 36, around 7 minutes until it reached the main site and produced a strong signal in radar reflectivity. Yeah, so clearly visible in the radar reflectivity. In red, that is the flight track of the tethered balloon system, and we can now look closer to the in situ data, what we measured on the balloon. So first, the aerosol measurement from the POPs instrument. Yeah, we had a background at around 200 cubic centimeters, and during the seeding event, 2 to 3 times higher. So we calculated seed concentration by background corrected aerosol concentration. And for ice crystal, we had nothing in the background. It's measured by HOLIMO and holographic imager. We had nothing in the background, and then during the seeding went really up to a few thousand, very high ice concentration. And here you see it once the measured ice crystal number concentration in orange, and an aggregated adjusted ice crystal number concentration, where we count how many heterogeneous ice nucleation event happens. And like if an ice crystal is aggregated out of 3 crystals, it counts as 3 nucleation events. I will come a bit talk a bit more about it later. And also droplets, where we see the Wegener-Bergen Eisen-Findeisen process really active. So during this high ice crystal concentration, we also had a strong reduction of cloud droplet number concentration, sometimes until full glaciation. Okay, overview, what we did. So overall, 78 glaciogenic seeding experiments. From 44, we had radar signals, and the temperature range between -10 and -4.6. The right, you see the reflectivity ordered by residence time of 2K band radars, and they're quite agreeing. And you also see, already a stronger reflectivity if longer residence time, so ice crystals grow bigger over time. And we also see the first signal after 3 minutes, quite early. And we have now analyzed 24 seeding signals in situ data. We might have 62 with in situ data, but it needs more time to analyze it. Okay, first thing we want to quantify was the ice nucleated fraction. So what is the fraction of the seeding particles forming ice? And what we actually measure is here, and here these are just made up numbers out of this my schematic. We have here 6 ice crystal measured, and the seed concentration, which is just the aerosol concentration not in the ice crystal of 8. And what we actually want to know is how many formed ice, and it was here 10. So we need an algorithm to say in aggregated ice gets us the number of monomers, and Yuin Zhang developed this algorithm, and which is we come back to have this aggregated adjusted ice crystal number concentration, which in this case 10 per liters, and we calculate the ice nucleating fraction by taking this into account. So in our example, it would be an ice crystal number concentration of 0.55, 55%. I give you a little bit time to follow this calculation and also think about what do you think, what is our ice nucleated fraction in the experiment? Is it 50%, 100%, 1%, 0.1%? Okay, the answer is it's around 1%. But first, look at this graph. So it's the seed concentration via the ice crystal number concentration. And we see, I would say for field data, a perfect correlation. So more seed concentration gives also more ice crystal number concentration. I was expected at some point a plateau. Haven't seen this. We have in all experiments only not 1 but 15 experiments. This is very good correlation, and this allows us to calculate an ice nucleated fraction per experiment because the correlation is so good. And Anna Miller then looked at 15, I think, different experiments and found, yes, at lower temperatures, the ice nucleated fraction get higher, so the particles are more effective, as expected. We see with longer residence time a lower ice nucleated fraction, and think that is a measurement artifact because aggregation removes ice crystals, sedimentation removes ice crystals, and at some point also the aggregation adjustment is not accurate anymore. And we saw no evidence as a connection or correlation to cloud droplet number concentration. And for us, the conclusion is so we have no evidence for contact nucleation. We compared then our ice nucleated fraction in blue to laboratory measurements, and notice that they are at the same temperature lower than the immersion freezing experiments. And we think that is because in the immersion, when you go to the lab, you have really strong supply of water vapor. First to create the droplets, to activate the droplets, and also later on when the ice crystal grow, you're already at a relative humidity of 100%. Here in our cloud, actually, we inject the particles to an existing cloud, so they probably not experience a really high supersaturation. So rather, they're getting dilution droplets, maybe not even activate. And then when an ice crystal forms, the relative humidity goes even down below 100%. That is the Wegener-Berschen-Findeisen process, and stops then nucleation of more particles. So here is the effect why it differs in field experiment. They have really limited water vapors. Okay, the next we're looking in is the diffusional grow rate of calculation. Here we want to know how big are our particles that we can measure with HOLIMO and how long have they grown. Yes, but what we have for measurement is only the residence time and not the growth time. So we assume we have no nucleation time is 0. So directly after IMP injection, ice formation happens. And I think we haven't seen any indication that is not a good assumption. We see a radar signal after 3 minutes, and yeah, it is here not nucleation, contact nucleation, where the aerosol particles have to find a particle, but it is immersion freezing, which should happen much faster. Yes, and we only look at the pristine ice crystals because then it's really comparable, the size of the ice crystal, how large they grow. And also the bit theory here, how it is process parameterized also in models. So not here since the growth rate in mass. It depends on main driver is the saturation with respect to ice. It's a very central point, but no one can measure it. That is always an issue, and you will see later also for us. Would be so good to measure that in a so precise that it's helpful what happens what happens inside a cloud, how fast do ice crystals grow. And then you have two constants before. One is a ventilation coefficient. It takes into account that falling particles grow faster due to ventilation, and a capacitance constant which takes into account the non-spherical shape of ice crystals. And we will later use this in the model study to do sensitivity studies by changing these two parameters. But first, what did we measure? So we looked at different experiments again. Every line is an experiment, and we sorted them by ice crystal number concentration. And we saw if we have regions in one experiment with high ice crystal number concentrations, the growth rates are smaller because you have less water vapor. So the ice crystal fight for the existing water. Yeah, you see a strong temperature dependence. Lower temperature have higher growth rate. And we also excluded the dashed experiments where we have strong rhyming and something weird happens. So we only look at the at the solid lines. But when you only look at the first part, the gray part, so ice crystal number concentration from 1 until 300, it looks much more constant in each experiment. And then Christopher Fuchs also looked at the liquid phase. Here, normalized growth rate. So he normalized all experiments to the mean growth rate per experiment. And the growth rate, yes, stays constant when you have enough droplets, but somewhere below 100, it's also seen that the growth rate gets limited because not enough droplets are present to provide vapor for the growth of the ice crystal. He also then compared this to literature data, laboratory measurements. So all the literature is the black dots, and our measurements are in the box plots. The gray box plots are all our data, where the growth rates are quite lower than measured in the lab, because we have a limited water supply. First thing was in blue, he applied a threshold-based filter approach, where he only looked at the parts of our plume where cloud droplet number concentration are above 100 per cubic centimeter and ice crystal number concentration are below 100 per liter. Yeah, and it gets surprising. It got not too much more, was still quite below the laboratory data. When there's no blue box plot shown, there we didn't have enough ice crystal left after the filtering. So we think that blue is quite good. It's quite representative for a secondary ice production region where ice crystal number concentration are high but are below 100 per liter. And as an upper bound for ice crystal grow rates, he used the lucky ice crystal approach. So just look at the largest 20% in red. And we see the best agreement with laboratory studies, but you also see a small underestimation of the growth rate, or our growth rate are a little bit smaller. Okay, so does the model reproduce our results? Nadia Omanovic using icon model in large eddy mode. So with a two-moment microphysics, a seeding parameterization, which is active also at high temperature like -5 degrees, a resolution of 65 meters, and a model time of 0.5 seconds. And she's emitting 1 million seeding particles per cubic meter per second for 6 minutes. And really, on the right, you see reproducing our field experiment. So that is actually how we see that also, like along a line. And here's our field side, and the wind comes here from the right and brings the plume over the field side. And the dots would be where the tethered balloon measured. And she chose 5 experiments, all having a similar temperature, but different growth time. And in the name here, this number is the growth time in minute of the experiment. And first we double check, can they produce the ice crystal concentration? And so yes, all with this seeding, or the model produce the same ice crystal concentration, but the ice crystal were smaller. So here's the growth rate in the model in the greenish color and in measurement in gray for all ice crystal number concentration, only for the small and for the really high ice crystal number concentration. And then she did sensitivity studies by changing the ventilation coefficient. And she needed really to enhance the ventilation coefficient by a factor of 3 to come nearer to our measured growth rate. And it's a bit interesting, in the measurement, you see that at the low ice crystal number concentration, the ice crystal number concentration, the growth rate are higher, but in the model it doesn't change much. The decrease in high ice crystal number concentration, both model and measurement show. And here that is a bit an indication that some small inhomogeneities are in the field, but not the model doesn't catch it. That maybe here some ice crystal grow really faster and some not so fast, and here model treats all the same. Okay, the growth rate didn't match, so we were even pushed them even harder. So not only change the ventilation coefficient, but up to 3, but also the capacity constant, reduce it to 0.5 to try to get its matching. And then looked what actually is the liquid water content doing. And that is one experiment where you see the reduction in liquid water content for the best match to the growth rate. So ice crystal grow as fast as observation, which is shown here, but the liquid water content reduction is, oh, sorry, I start again. So ice crystal grow as fast as observation, and here we now compare the reduction in liquid water content between the model and observation. So the model shows 10% reduction, and the observation, which are at this time where it's here gray, show a much stronger reduction. Only if we would go to the fastest grow rate, so I really tune these two parameters to the extreme, we could reproduce it. But that would mean the ice crystal would probably grow too fast. So somehow we cannot match it. Yeah, there is a conclusion, and it's not as clear in the other 4 experiments, but often is the observation between the matching grow rate and the fastest grow rate. And we think, yeah, there must be some difference in the water vapor field, that in reality you have stronger turbulence and larger scales of inhomogeneity, which a model, even at a high resolution at 65 meters, cannot catch. But it would be interesting to make more model study with fine resolution. Okay, last part is aggregation rate. Here we take into account that we know from this algorithm how many aggregation events this ice crystal was created. Here it's quite simple. There was one aggregation event, 2 ice crystals aggregated together. And we can calculate it for a whole volume. What is the number of aggregation, and use the residence time where it has to get a rate and say, okay, in this time, how many aggregation happened in this volume. So we looked at 24 experiments. You see a decrease in aggregation rate with longer residence time. That is probably because the bloom get dispersed, and warmer ice crystals have experiment in a warmer temperature have a higher aggregation rate, and that's why we look next. We choose 2 experiments at the same residence time, but one is much warmer than the other. So here is the picture of it, and as is known, the one which is around -5 degrees, say you have columns, and in the cold experiment around -8, you have plates. And this leads, since the columns grow larger, has a broader size distribution and larger aspect ratio, that leads to a higher aggregation rates, and we're currently analyzing it more quantitatively to predict the aggregation rate in our experiments. Okay, and as Martina introduced, I'm always liking developing new instrument, and there's also a bit of an outlook what I would like to do next. That is, I'm still not satisfied only measure clouds at one time, but would do quasi-Lagrangian measurements of the ice crystal processes. And Sebastian Käser is currently developing a free-floating balloon systems where we can stay on one height with a balloon, and we would like to put a lightweight holographic imager on it to fly with an air parcel through the cloud and measure ice crystal processes. Okay, and with this come to an end. So I hope I showed you that we did quite large number of glaciogenic seeding experiment, and what is the cool thing about it, that we can start doing statistic out of measurement in natural clouds. We know when the ice crystals are formed, or at least when the aerosol particles, the IPs, are introduced into the cloud. We think the particles freeze via immersion freezing of solution droplets. We looked at the diffusional ice crystal growth rate and aggregation growth rate, could derive it from field data, and it compares quite well to also the laboratory data. And we did a sensitivity study where comparable growth rates did not reproduce a reduction in liquid water content because the vapor field is different in the model to do turbulence and inhomogeneities. And before I thank you, I want to thank my whole team here. Some impression from our field campaigns where we had some quite tough time in the cold, but also quite nice things, seeing then our produced ice crystals. And yeah, thank everyone for all the effort and work putting in, and thank you for your attention. Thank you.
Yeah, thank you.